Okay, so we just looked at these reactions. You can hear me okay? Oops. Okay, so let's get the pen going here. And okay, so this is the summary of all the reactions that we looked at on Monday. First of all, we've got lime as one of the chemicals. That's calcium hydroxide. And you can see it appears in 4 of those 6 reactions. And then we've got soda. And soda is soda ash, Na2CO3. And so 2 of the reactions are fed with soda ash. So you need to know what are the 2 chemicals that are used in a lime soda reactor or lime soda softener. Then the next thing is we've got certain anions and cations. So cation, cation, cation. And those cations are either calcium or magnesium, and because they're calcium or magnesium, this is hardness. And then we also have certain anions. And so here's an anion, there's an anion. So the particular anions that we have are bicarbonate, sulfate, and chloride. And the bicarbonate, sulfide, and chloride are the various species of hardness that can enter into, that need to be treated, right? So we've got calcium bicarbonate, we've got magnesium bicarbonate, magnesium sulfate, magnesium chloride, and calcium chloride. Now then we've got this bicarbonate, HCO3, and bicarbonate is what we call, it's a form of alkalinity. So alkalinity also has 2 other forms, and you guys have done a P&M alkalinity test, and you've probably done several of them. And in the P&M alkalinity test, we can determine basically all 3 species of alkalinity. Everything that we call alkaline, we can determine using a P&M alkalinity. So bicarbonate is one form of alkalinity. What are the other alkalines, or alkalinities?
Hydroxide.
Right on. Okay, so hydroxyl alkalinity or OH alkalinity. And there's one other one. One more. Okay, that's carbonate alkalinity. So we know the calcium bicarbonate is not only hardness because it's got the calcium, but it's also alkaline because it's got the bicarbonate. And similarly, magnesium has the bicarbonate, so it's alkaline. And it also has the magnesium, which is hardness. So this stuff here is both hard and it's alkaline. And because it has the HCO3, we call this temporary hardness because it does not persist over 100 degrees Celsius. So it's temporary hardness. Now, then we also got some other hardnesses here. So we've got sulfate ions, we've got chloride ions. And those anions or a permanent hardness, which means that they do form scale, but they precipitate and form scale at higher temperature, greater than 100 degrees Celsius. Okay, so it doesn't matter which species of hardness we're talking about, temporary or permanent, it's all going to form scale. If it gets to the boiler, it's going to form boiler scale. However, the permanent hardnesses are not alkaline. Only the temporary hardness is. And temporary and permanent hardness are words that you need to know. I know that they weren't used last year in 4th class. They probably should have been introduced then. I'm not too why that was left out of the curriculum, but it's important stuff. So what are the reactions? Both of the temporary hardnesses combine with calcium hydroxide. They form precipitates in either the form of calcium carbonate or in magnesium hydroxide. So that's a precipitate, that's a precipitate. And what this really means is that lime, which we know is calcium hydroxide, is used to eliminate temporary hardness. Temporary hardness. And so what do we get? We get calcium carbonate and magnesium hydroxide precipitates. And we also get water effluent. So think about this. What's coming in here is alkaline as well as hard. Alkaline because it got the bicarbonates. And what's coming out in the effluent side is pure water, which is a good thing. Well, that's it. There's no alkalinity, no hardness at this point. Anything that caused alkalinity has been eliminated through this chemical reaction. But what we do have is calcium carbonate flock, and we've got magnesium hydroxide flock, and that's all precipitated, and we're going to have to get rid of that. Now, as for the permanent species, so we've got magnesium sulfate and let's look at the magnesium sulfate first. I was saying that the lime is only for temporary hardness. It gets rid of temporary hardness. Well, it is also being used here. In this reaction, it produces a magnesium hydroxide flock and calcium sulfate, which is the same as this stuff here. So yes, we've precipitated the magnesium, but all we've done is converted this type of permanent hardness into another type of permanent hardness. So it's kind of like a wash, right? You go, well, why do we even bother? You know, all we've done is a double replacement reaction. All we've done is swap the calcium for magnesium. So it's basically we've done nothing, right? We have not removed the hardness at all. All we've done is change it from its magnesium form to its calcium form. Now, as for the magnesium chloride comes in with calcium hydroxide. Again, it forms magnesium hydroxide. And again, all we've done is a double replacement reaction where the calcium and magnesium pretty much swap places, leaving us another form of permanent hardness, which is calcium chloride. Now this is where the sodium carbonate comes in. So calcium sulfate, which was produced up here, or maybe it came in the raw water, or in both situations, maybe some was produced inside due to a reaction, maybe some of it came from the raw water, but regardless its origin, in the existence of sodium carbonate, what we end up with is sodium sulfate and calcium carbonate. We know that calcium carbonate is a precipitate, so it comes out of suspension, and then we just discharge it from the reactor. And as for the calcium chloride, again, we have the soda ash, and what we get products are sodium chloride and calcium carbonate precipitate. So what we're left with then, what is leaving the lime soda reactor or lime soda softener, is this stuff: water, dissolved sodium sulfate, and dissolved sodium chloride. And what we know about sodium compounds, they are highly soluble, number one. And number two, they do not form scale. They do not scale. So we're not too concerned about sodium compounds being in the boiler, other than this: both of these remain dissolved, so they are a component of total dissolved solids. So what do we have coming in? We had lots of calcium bicarbonate, magnesium bicarbonate, sulfates, chlorides, all of this stuff in. So we got alkalinity and hardness coming in. And dissolved solids. That's all coming in. And what we got leaving is water, which is not alkaline, nor is it hard, nor is it dissolved solid. And we've got sodium sulfate and sodium chloride. Okay, no hardness and no alkalinity. So on the effluent side, no hardness, no alkalinity. Is there TDS? Yes, but there's a drop in TDS. So this is theory. It's the land of belief, but it's important to know that alkalinity, hardness, and TDS coming in, and it leaves zero hardness, zero alkalinity, and much less dissolved solids. Okay, so that's a summary. Again, it's theory. You need to know those reactions. And so this is a good little slide that shows, basically summarizes it. So even though there's only a few species shown here, we could add magnesium bicarbonate. We could do that. And we can add calcium sulfate if we wanted to, and we can add magnesium chloride. But this here summarizes it well enough. That's all dissolved, and it's going into the lime soda reactor. The chemicals we add are lime and sodium carbonate, and we can also add maybe a couple more that we should list: a coagulant and a flocculant. Okay, so those are the four chemical inputs. We get precipitation going on in there due to the calcium hydroxide and sodium carbonate and their tiny little charged particles. They're basically colloids. The coagulant that we add makes them form a small little pin flock. The flocculant that we add brings it all together, and it forms this spongy sludge that accumulates somewhere on the bottom of the vessel. And so we're going to have to blow that off. So regular blow off as it accumulates, we'll be discharging calcium carbonate and magnesium hydroxide. As for the effluent, we get sodium chloride dissolved, yes. We get sodium sulfate dissolved, yes. And we could even add here that the effluent, of course, is water, right? Some of that water is coming in the influent, and some of it's actually formed due to the chemical reactions in the lime soda reactor. So, this looks a lot like a clarifier, doesn't it? Well, this is not a sludge contact clarifier, it's a sludge contact softener. And you can see it's really the same kind of piece of equipment, right? I mean, we've got influent water, and what we're going to do is we're going to meter it, put a water meter on it, and we've got some chemical feed lines here, so we're going to put, maybe solenoid valves, or maybe what we're going to have are flow control valves, or maybe we're going to start-stop chemical feed pumps. And so one of those is going to be coagulant, another one is going to be flocculant. There's going to be more, of course, there's going to be some lime being fed in a slurry. And if we've got permanent hardness, we're going to add soda ash. Which really takes me to this thing here. What if I don't have any permanent hardness in my well water? And that could very well be the situation. If I have no permanent hardness, then all we need to add is lime. So we've got some chemical feed lines, lime and soda, coagulant, flocculant, all going in, and they're going to mix with the water as the water comes in. Notice we've got the diverging cone, which is going to cause the stuff to slow in velocity. We've got some paddles on a shaft for mixing it. Just like we saw with the clarifier, we've got a bottom bearing for support, so we're going to put water in there to flush all the debris and sediment and flock that forms. We're going to make sure it doesn't get into the bearing, so we keep this thing upright and stable. And what we have is a sludge blow-off. And this one here, you can see the control valve. And so what we have is a brain, a controller that looks at the water flow. Okay, there's our controller, so water flow, and then it's going to send out control signals to the various control valves so that, blow off, chemical feed, all of this stuff is related to two things, the water chemistry and the actual influent flow. So as the water mixes, it descends through, pin flocks are forming, and heavier flock is forming as well. And then we get to this bed level where the velocity has slowed down so much once you get to about this point that these pin flocks and larger flocks simply cannot get carried through because the force of gravity at that point would be equal to the force due to velocity of the liquid. Remember, the liquid's slowing down because of this convergence. So at some point, we can't keep the stuff in suspension. The water that's flowing, gravity's pulling down and pulling all of this sludge down into a concentrated area where our backwash valve, or pardon me, our blowdown valve can open up and discharge the sludge as it builds up. So this has another feature too. So I got a backwash, or pardon me, not a backwash, a blow-off valve that opens up intermittently, discharges sludge. But now after it opens, we're going to have this line that's all full of sludge, and the sludge is going to settle inside of the pipe and it's going to plug off the pipe. So every time after this blowdown valve operates, immediately afterwards, a backflush valve is going to open up and it's going to put pressurized water basically to clean out the line. Okay, very, very common. And if you work in a SAGD plant, you'll see that. Instead of having multiple sample points, this one here has got this swing pipe. So when you have it in this position, it checks the density of the bed at the top, or the level of bed at the top, and progressively lowers zones. And we saw that with the clarifier. With the clarifier, we had these 4 sample points, and we would fill up a graduated cylinder, and it would inform us about the height of the bed and the density of the bed and all that kind of stuff. So again, we do the same thing with the lime soda reactor as we would do with the clarifier in terms of monitoring the bed level, monitoring the bed height. Now, here you can see from the generating station, here's our lime reactor, or you can call it a lime softener. And notice that it does not say lime soda, because where I worked, the amount of permanent hardness was pretty negligible. And because of that, all we did was we fed lime. That's all we needed to do. If there was permanent hardness, it was a very small amount, and that got dealt with our ion exchangers. So let's take a little look right now at what we have seen so far. What we can have is either a clarifier, if we're using surface water, or we can have an aerator if we've got groundwater with iron. Then what we're going to do is take the water from each one of those with a pump, so we've got to repressurize it, and we're going to pump that water into our lime reactor with a bunch of chemicals that go in there, and that will go to the bottom forming sludge, and the relatively clean water now that's quite a bit softer will overflow into another tank that we call the clear well. Okay, so the clear water flows over into the clear well and sort of accumulates in there. So you have sort of like a water reservoir. Then what we're going to do is we're going to repressurize it. That's why we got a pump here. There's another pump. Well, there's a standby pump somewhere. I can't see. Oh, here. Yeah, there. Okay, so we've got standby pumps and a regular pump, and that's going to put it now through the series of pressure filters that we looked at on Monday, and the carbon filter. And from the pressure filters and carbon filters, we're going to go into an ion exchange units. So we're going to have a cation exchanger. Then the water is going to go through an anion exchanger. We'll have a mixed bed demineralizer on there, and we'll get to that a little bit later in class today. And then it goes to feed water storage tank in the plant where I worked, or it could go to a deaerator, followed by the boiler feed pump. You get the idea, you know the drill. Okay, so this is makeup water. And what we've looked at so far is the clarifier or the aerator. And then we looked at the lime reactor, lime soda reactor, clear well, and we've also looked at the pressure filters. Make sense so far? Now, I'm not sure if this is going to work. Here, you can watch this. Now, this is a video that I took at the Brandon Generating Station in Manitoba. And what you're looking at right now is the motor and the gear drive that drives the agitator. Okay, so there's a scraper on the bottom, and then there's numerous paddles that mix the chemicals with the water. Now, this is the mixing zone that you're looking at, and it looks very, very milky due to the existence of lime, and there's a lot of precipitation going on there. Now, very shortly, we're going to walk over to the other side, where these people are standing, and we're going to look at the other one that's in service as well. You can see on the left and on the right, there would be powder mixers. So we've got bunkers up above. One of them is full of lime, the other one is full of soda ash. And these two are going to measure out how much lime and how much soda go into mixing tanks that are below. And then from those mixing tanks, they're mixed with water and pumped into the lime soda reactor. Now this particular lime soda reactor, you can see in the middle where the reaction is taking place, and you can see the relatively clear water that surrounds it. Okay, there's the relatively clear, and it was made by a company called Infilco, and they call it Accelerator. That's what they call it at Brandon. So anyway, that's that for precipitation softening. So that's one type of softening that we do, precipitation softening. The next thing is we're going to go into ion exchange softening. So the next one here is the hot lime soda softener. And this one here is the exact same reactions. However, the reactions complete faster. I mean, so normally the higher the temperature, the faster the reaction. As well, the reactions are driven closer to completion. The reactions are closer to 100% efficient. Now, typically what we have is in a cold lime reactor is we add a certain amount of lime soda and we add a certain amount of excess of reactants to help drive the reaction to completion. But we can use less excess reactant with a hot lime softener. Also, because the fact that this thing is operating at a very high temperature, it deaerates, and it also removes silica. Actually, better to say it reduces silica. Reduces silica, and we know we don't want silica in there. So let's take a look at this thing. Here's some interesting things about this particular drawing. First of all, it shows the meter at the raw water inlet. And of course, that meter is going to operate the chemical feed. What else have we got going on here? We've got a particular level in there. And so we've got a level control that controls the amount of influent. Now we've got a steam inlet that's heating up this stuff as it comes in. So you can see it actually deaerates with the steam. So we have a vent and actually a vent condenser as well, so we don't lose too much steam going out the vent. Really what we got going out the vent is going to be CO2 and also oxygen because it does have this deaerating effect. What else have we got going on here? Here are some after filters, because if we get any particulate carried over, and of course we always do, then these are going to filter it out prior to it going to some sort of a storage facility, or maybe it's going to go, instead of to water storage, maybe this softened water is going to go into a demineralizer bank or a reverse osmosis system in order to give it the final polish. So whenever we've got a precipitation softener, what we're looking for is something that will remove the bulk of the hardness, and that makes it easier on the downstream equipment. So if we've got ion exchangers downstream from that, it won't load them up heavily with hardness. No, we got most of the hardness taken care of with one of these lime soda reactors. So the water comes in, we got a level control, water goes out. Now the water that leaves gets filtered, And in this case, they're showing it's repressurized in the way that it goes. By the way, because this is pressurized with steam, what we have is an ASME code section 8 pressure vessel. And so it's going to have relief valves and all that kind of neat stuff. And what else can we say? Let's say that this is going around 110 degrees Celsius. Okay, or maybe hotter yet. So other than that, it's really the same as a cold lime soda reactor. One other interesting thing is we've got this backwash pump down here. And so when it's time to backwash these after filters, we're going to take water from the, and that's water, most of the sludge blankets down here, right? So we're going to take this water just where the treated water effluent takeoff is, and we're going to take that softened water and we're going to use it to backwash the individual filters when they require backwashing. Now the effluent from these filters, the backwash effluent, actually goes back into the vessel. So we conserve water in that way. Now for ion exchange. And so you know about this here. You have studied the sodium zeolite softener. Today what we're going to do is going to get into the hydrogen zeolite softener. And then we're going to look at the anion exchanger, which we call an R.H softener. So each one of these is an ion exchanger. So for example, in the first one, if I've got some calcium bicarbonate temporary hardness going into the vessel with the sodium zeolite beads, what we get coming out is sodium bicarbonate. And what stays behind on the bead is going to be calcium zeolite. Then when we regenerate it, we take the calcium zeolite plus a very concentrated sodium chloride solution. And what we end up with is, again, well, there should be 2 sodium zeolites. We end up with Na2Z plus calcium chloride, and the calcium chloride is going to go to waste, down the drain. As for the hydrogen zeolite softener, it's the same type of thing where we've got, again, this form of temporary hardness coming in, plus the hydrogen zeolite is going to actually give us carbonic acid. And calcium zeolite. Or let's say we've got something else going in. Oops. Let's say we've got magnesium chloride as our form of hardness. This would be permanent hardness, plus hydrogen zeolite is going to give us magnesium zeolite plus hydrochloric acid. Okay, so those are 2 of the softeners that we're going to look at. And then the last ion exchanger was the R.OH. And so let's say that the hydrogen chloride from the previous reaction plus the R.OH is going to give us R.Cl plus H2O. So these are the ion exchanges that we're going to be going through in terms of theory, and then we're going to look how we combine this stuff. Now, one of your objectives is to know the ions, objective 5. So there's your ions. So you know we got cations and we've got anions. In this case, the anions that you see are all polyatomic. So you need to know these, and you also need to know the common name. So HCO3 is bicarbonate, SO4 is sulfate, and on and on and on. So you need to know that stuff. So starting off with sodium zeolite, and you know this stuff, but here, for example, is a bead. This is from the Suez handbook, and the zeolite beads, the little resin beads, are mostly water. They're very hydrated. They're made of plastic, so it's a type of polystyrene, and what it has on it are a whole number of transfer sites all over the surface of the bead. And so when water comes in with some sort of a calcium, the calcium goes to the site and the site gives off a sodium ion. Or maybe if it's a hydrogen zeolite softener, it'll give off hydrogen cation. So here's our sodium zeolite softener. You should know how to regenerate it, how to rinse it, how to put it into service. So let's say I've just regenerated one and all those beads have got transfer sites that are now loaded up with sodium. What I need to do is rinse it down, and I'm going to rinse it until the hardness gets really low. So there's hardness on the y-axis. So maybe, I don't know, maybe that's 0.5 parts per million. At that point, I'm going to put it into service, and the hardness is going to continue to drop, and then it'll stabilize. It should be pretty much zero. And then we reach something called the end of the run. So between those 2 points, what we have is called a service run. Now with a pressure filter, we know that there's a delta P, and when the delta P reaches a certain point, our filter is considered to be kind of plugged up, and what we want to do is backwash and put the filter back into service. In the case of a sodium zeolite softener, the end of run is not indicated by delta P, it's indicated by what we call hardness breakthrough. Okay, so there's our hardness breakthrough. And what we're going to do is try and stop the softener, get it out of service right when hardness breakthrough occurs, and then what we're going to do is regenerate it. Because downstream of that point, well, that's when most of the resin has given up its sodium ions. And what we start to see then is an increasing amount of hardness in the effluent. So when we start to see some hardness in the effluent, then we know we're at the end of the run and we need to take it out of service and regenerate it. And so then those are the exchange reactions on the top, and then there's the regeneration reactions on the bottom, and you do need to know these. You should also know the life cycle of the sodium softener. So it's in service, it reaches the point of exhaustion, and we can determine that by looking for hardness breakthrough. At that point, we take it out of the service, we backwash it, just like we did with the pressure filters. We need to expand the bed. And if there's dirt, we're going to release dirt. And the whole idea here is we're trying to expose the maximum surface area of the beads so that once we start adding the brine and regenerating it, then the entire bead surface can be exposed to the regenerant material. So if it's sodium chloride, then we want everything exposed to sodium. Then we will slowly displace the regenerant chemical. and sometimes we call that slow rinse. Then we're going to do a fast rinse, and the fast rinse is very important for us because it recompacts the bed. And recall that we want the bed to be compact, reduce channeling. After we do a fast rinse, we vent it, get the air out of it, and we put it back into service. So you need to know this. And partly you need to know this because even though we've been talking about sodium zeolite, it's the same thing with a hydrogen zeolite softener. So why would we get a short service run? I mean, what we would really like is a nice long one. We want to know that we don't have to use lots of chemicals to continuously regenerate this thing. If this is a 100,000 grain per gallon softener, and we're putting in water that's 200 grains per gallon. So let's say we've got 100,000 grain softener, 100,000 grains. And the water that we're treating is 200 grains per gallon. Per gallon. So then how many gallons should be 200 grains per gallon. 200 grains. So 200 grains per gallon. So how many gallons should I be able to treat? I should be able to treat 1,000 over 2. I should be able to treat 500 gallons of water. But a short service run, maybe I can only get 300 gallons of water, and then I start to see that hardness rise and go, well, what the heck? Why was my service run so short? So this is very important. You should know this stuff. Number one, maybe I've got improper flow. Maybe I've got channeling going on. And channeling can be a result of excessive flow, or it can be low flow. Either one of those situations could make water try and go through the path of least resistance. Number two, this is probably the biggest one, improper regeneration. So we need to regenerate with a particular quantity of brine, and that would be according to the manufacturer. And that depends upon how much bead, how much resin the thing holds. And was the brine strong enough? According to the Suez Handbook, should be 8 to 10% sodium chloride solution. Now, number three here is attrition, which really means loss of beads. So how do we lose resin? We backwash too hard. Or maybe what happens is the resin fractures, and a certain amount of resin fractures every single year. And I read somewhere, and I can't remember where it is, but I read somewhere, and I've been trying to find out 3% attrition loss per year. That means 3% of my beads are lost due to mechanical damage. They turn into very fine beads. They go with the backwash, which means that I lose 3% capacity per year. So that's normal attrition loss of materials. Or maybe I've got water collecting pipes inside that are fractured. And so if I've got a broken pipe inside of this thing and I do a backwash, or even if I have it in service, I can be carrying beads out of the softener, which is a problem. Now, this is another biggie here. I'd say this one here is right up there with improper regeneration, which is inadequate backwash. You didn't have enough backwash flow, so it did not expand the bed before regeneration and did not expose the beads to the regenerant. Or maybe you didn't backwash it long enough. Okay, maybe the backwash should have been for half an hour and you shortcut it. You're looking for cuts and you did it in 15 minutes. Well, you're not going to get enough exposure of the beads to the regenerant material, to the brine, and so it's not going to get a proper regeneration. Number 5, iron fouling or organic fouling. Number 6, chlorine. Chlorine actually damages the polystyrene beads and causes them to fracture. And 7 is excessive inlet water turbidity. So what that means is that there's just too much suspended matter going in and it covers the surfaces of the beads so that we lose some of those ion exchange sites. Now, this is all under sodium zeolite, but I got to tell you, this all applies to hydrogen zeolite, except for this sodium chloride comment. Okay, it doesn't matter whether it's a hydrogen zeolite or a sodium zeolite softener, they're both affected by the same things. So here you can see beads that are fouled with iron, and here you can see some that are fouled with organics. But now it gets more interesting. We're going to get into hydrogen zeolite, and we use the same beads. The only difference is we're going to regenerate it with sulfuric acid instead of sodium chloride. Now, very, very important point. The reason we do this is to get rid of alkalinity. The worst alkalinity of the bunch for us is the HCO3 or bicarbonate alkalinity, because when that stuff gets into the boiler, it decomposes and forms CO2 gas and water. And so basically it decomposes the CO2 as a gas, and it goes with the steam, and it causes condensate line corrosion. So alkalinity corrodes condensate lines. So a dealkalizer uses hydrogen zeolite softening to get rid of alkalinity. Now the problem is, because it's hydrogen zeolite, what we get coming out is acidic. So we're going to get carbonic acid, hydrochloric acid, and sulfuric acid. So when we were looking at the sodium zeolite softener, we talked about when is the end of run, and we said the end of run occurs when hardness breakthrough occurs. Well, this one here, we're going to look at free mineral acidity, or FMA. And mineral acidity, FYI, mineral acidity is due to the presence of quote-unquote strong acids. And strong acids have a pH, and this is just a broad comment, okay? I could be precise, but probably depends upon the literature. So let's just say it's a pH of lower than 4. So what we get going in is, say, calcium bicarbonate as our temporary hardness. And maybe we got some magnesium chloride going in as a form of permanent hardness. And maybe we got some calcium sulfate going in as another permanent hardness species. When these go into our hydrogen zeolite softener, what we get is carbonic acid. That's what the calcium bicarbonate becomes. We get carbonic acid in the effluent. We get sulfuric acid, because that's what the calcium sulfate becomes. And the other thing is we get hydrochloric acid, because that's what the magnesium chloride becomes. These last two, the H2SO4 and the hydrogen chloride, these are mineral acids. And when we're doing an FMA test, free mineral acidity, that's what we're testing for, pH less than 4. So let's go back to this hydrogen zeolite softener. We just finished generating it and we rinsed it down and we compacted the bed. So now what we're going to be doing is putting out lots and lots of acid. Acid, 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 acid. Well, when we reach the end of the run, that would mean that we're kind of running out of hydrogen ions. So some of the calcium, some of the magnesium is going to be going through unchanged by the hydrogen zeolite, which means that the amount of acid that we produce starts going down, 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 right? The free mineral acidity, we start losing free mineral acidity because we've run out of hydrogen ions. So how do we know the end of run? We do tests. We test the water for free mineral acidity, and once the free mineral acidity drops to below where we're supposed to have it, that signals end of run, and we regenerate it, but instead of using sodium chloride, we're going to use sulfuric acid. So here are the reactions. Calcium sulfate, which is permanent hardness, plus hydrogen zeolite gives me sulfuric acid and calcium zeolite. Let's say sodium chloride comes in. Well, because the sodium is not a form of hardness, so this is just a dissolved solid. This dissolved solid comes in with the hydrogen zeolite, becomes hydrochloric acid and sodium zeolite, kind of weird. And then we got this temporary hardness comes in, calcium bicarbonate, plus the hydrogen zeolite gives me carbonic acid and calcium zeolite. And so now you're wondering, what's the big deal? Why do I want to use hydrogen zeolite? Because it's giving us acid in the effluent. That's going into my boiler. And didn't you tell me in corrosion, Dave, we don't want acid in our boiler? So what we got to do is deal with this. By the way, this is not alkaline. This is not alkaline. This one here, yes, it is alkaline. And we don't like alkalinity because it destroys our condensate lines. So what do we do? Well, first of all, we never use a hydrogen, well, we rarely use a hydrogen zeolite softener on its own. Let's just take a look here. Now this is, this picture shows up in Objective 8 of the PanGlobal, but it's wrong. It shouldn't be under Objective 8. It should be in Objective 7. So here's our hydrogen zeolite unit. And we got raw water coming in. Those ion exchanges occur that we looked at, and they're on the right here too, and the acids are showing up in bright red. So downstream of the hydrogen zeolite softener, we've got plastic pipe, because plastic, of course, is corrosion resistant. Then we're going to put that thing into, first of all, a degasifier, which is really, it's an aerator. Just like we saw for getting rid of iron, the degasifier has got a blower. It's got all these trays. The water cascades over it, breaks up into small particles with a large surface area. And what we do is we expose it to oxygen. And in doing so, we take the carbonic acid, this stuff here, and we convert it into CO2 and H2O. So this vent to atmosphere carries away the CO2. We've just gotten rid of the carbonic acid. Because we got rid of the carbonic acid, we now have no alkalinity. We just got rid of it. So whenever you see a hydrogen zeolite unit installed anywhere, It's because you want to get rid of alkalinity. That's why you use it. But then we've got free mineral acidity down here that's going to go to the boiler. So the FMA includes sulfuric and hydrochloric acid. So what do we do about that? We take an alkaline neutralizer. As a matter of fact, it's going to be NaOH solution, sodium hydroxide. And we're going to drip some of that sodium hydroxide in an ongoing basis into here, and it's going to neutralize the FMA. So what goes off then may actually have a little bit of excess hydroxyl ion, and we do know that that is alkaline. But even if it has a little bit of excess OH, that's okay because we want that in the boiler anyway. So these are the neutralization reactions. So the dilute H2SO4 down here in the storage area combines with sodium hydroxide, sodium sulfate and water, and the hydrochloric acid that forms combines with the sodium hydroxide, giving us NaCl and H2O. And if you notice that these, I think, are the two things that come out of the highly soluble salts that come out of the lime soda reactor as well. So that's the simple use of a hydrogen zeolite softener. It cannot be used on its own. You have to be able to neutralize the acid that leaves it. In this case, we neutralize the acid with the degasifier for the bicarbonate or the carbonic acid, and with the sodium hydroxide drip. So objective 8 is about a dealkalizer, and actually this is described in objective 7, which is really confusing. Okay, this picture here, this illustration, shows up in objective 7, and the description is in objective 7, but for some reason PanGlobal stuck it in the description and this picture are in objective 7, really belong in objective 8. So here's what happens. The raw water comes in and goes into the H2Z, and what we get coming out is acid in the form of HCl, H2SO4, okay, and also some carbonic acid. And so what's going in? We've got, say, magnesium chloride, permanent hardness. We've got calcium bicarbonate maybe coming in as temporary hardness. And maybe we've got magnesium sulfate coming in as permanent hardness. So this stuff here is in the raw water, and it's going to turn into these acids. But some of that water is also going to go into a sodium zeolite softener. And what comes out of there is we've got sodium chloride. We're going to have sodium bicarbonate, HCO3. And we are going to have sodium sulfate. This stuff here is coming out of the sodium zeolite softener. But remember that this stuff here, NaHCO3, is alkaline. And so it's it got a high pH, or higher pH than we can use it to neutralize acid, basically. So we take some of the effluent from the sodium zeolite, and the baking soda, the sodium bicarbonate, is actually going to neutralize all of those acids, as long as we've got the right proportion. So we have to have a particular flow going through the sodium zeolite and a particular flow going through the hydrogen zeolite. And then what we're going to have is a three-way valve here, a blending valve, or a mixing valve. And the mixing valve is going to combine those flows in the proper proportion so that all that we get out here, the only kind of alkalinity is going to be carbonic acid. So we're going to put a degasifier tower downstream to neutralize the carbonic acid, and away we go. So those reactions are here in this slide. So this is one of the things we got from the sodium zeolite softener. That's the sodium bicarbonate. This is what's coming out of the hydrogen zeolite, hydrogen chloride, sulfuric acid, and they're showing nitric acid too. When you combine both of those flows, what we get is sodium chloride, sodium sulfate, and sodium nitrate. And then the other thing that we get coming out is carbonic acid. The carbonic acid goes into the degasifier, it decomposes, the CO2 is vented to the atmosphere, and what we should have here is zero alkalinity and zero acidity. So what have we done then? We've had TDS comes in, and leaving we've got a reduction in TDS. We have alkalinity comes in, and we should have zero alk out. Now we're going to check this here for free mineral acidity as well, and we might add a little bit of hydroxide in there to neutralize it. Okay, if necessary, maybe just a small amount of sodium hydroxide. So we may actually have some alkalinity leaving. And as for hardness, well, we had magnesium and calcium coming in to both of those units, and what left is zero hardness. Now, what's very, very critical is we have to have the proper blend all the time. So if we have too much too much flow through the sodium zeolite, then we get an alkalinity up, because we're going to get too much sodium bicarbonate coming out of the sodium zeolite. And if we have too much through the H2Z, then what we're going to get is acidity is going to go up. So that's why it's very critical that we test it all the time, that we test this for free mineral acidity. We maybe do a PNM alkalinity test on it. Whatever, we are monitoring this all the time and making sure that we've got the blending valve set so that we get the precise amount of flow through each one of those two units. So you can see why we call it a split stream. We split the stream here into two different directions. So there's certain advantages to it. We get soft water. It should have low to zero alk. It's reasonable in terms of its installation cost and its operating cost. and we do get a reduction in TDS. Notice that the sodium zeolite does not reduce TDS, whereas hydrogen zeolite does reduce TDS. Now, as for removing all of the alkalinity, again, in theory it will, but of course it's got that temperamental blending valve, and if we get too much flow through the sodium zeolite, we will get alkalinity. If we've got a system that's very temperamental about silica, it doesn't do anything. To get rid of silica, what we need to have is an anion resin. That's how we get rid of the silica. And the very fact that we use this decarbonizer, or which we also call a degasifier, or we can call it an aerator. Well, and that's what it does. It aerates. So it's adding dissolved oxygen, and really this increases the load on the deaerator, having oxygenated water. Some people call these things a poor person's demineralizer. They don't actually demineralize, but that's our very next thing, is the demineralizer. So here you can see a, this is the place where I used to work, Selkirk Generating Station. So what we have is a cation exchanger, and we've got an anion exchanger, followed by a mixed bed exchanger. So we're going to take a look at each one of those. So what we have is a system that exchanges all of the cations for hydrogen. So it's a hydrogen zeolite softener. And then it exchanges all of the anions for hydroxyl ion. So let's say that we've got hydrogen softener. What we got coming in maybe is magnesium chloride, or maybe we got calcium bicarbonate. When those go into our hydrogen zeolite softener, what we get is hydrochloric acid, we get carbonic acid, and we also get calcium or magnesium zeolite. So that stuff's staying behind. Well, we kind of messed that up, right? We've exchanged the cations. Okay, that's a cation, that's a cation, and we've exchanged it for that. And so what we've done is cation exchange. But now we got to deal with this acid again. We don't want the acid. So we're going to take the acid, we're going to put it into the anion exchanger. So maybe we've got some hydrochloric acid going in. Maybe we've got some sulfuric acid going in. Carbonic acid going in. And in this case, the resin is called R.OH. I know I got it backwards here. I just ran out of room. So R.OH. And so now what we're going to do is exchange the anions. And we're going to exchange the anions for hydroxyl. So what we end up with then is H2O and R dot Cl SO4 CO3. That's a 2 minus, that's a 2 minus, that's just a 1 minus. Well, this is our only effluent then, pure water effluent. So what we have then is a hydrogen zeolite softener in series with an anion exchanger. And that's what you see here. So we've got water that comes into here from the pressure filters and from the lime soda reactor. So most of the hardness has been removed and it's been filtered so we don't have any particulate. And so from the cation exchanger, what we have is acid, leaves, it's acidic water. Notice that the pipes here are plastic. The acidic water goes into the ion exchanger, and what comes out is pure H2O. Now, as a final polish, we've got this mixed bed exchanger that has got both anion and cation resins all mixed together in a common bed. And then what leaves is water that is equivalent to water that has been distilled 10 times over. So conductivity is a good measure of impurities in water. This water will have zero conductivity. Because we have removed all of the cations and all of the anions and we've exchanged them for H and OH, we get no alkalinity. And if we use a SAC, an SBA, strong base anion exchanger, if we use an SBA, we will get very little to no silica because it will actually remove the silica as well. So it sounds complicated. There's a lot of equipment, as you can see. This is just one bank, so there are two of them side by side or maybe multiples. And the whole idea is that we can regen one while the other one is online. And depends upon the size of the plant and how much their makeup water requirements are. There might be several of these banks, all in different stages of being in service or being backwashed or regenerated. So you think, this must be pretty expensive, but it actually turns out to be less expensive than distillation, even when we factor in the cost of chemicals and all that kind of stuff. So that's why they use it. Otherwise, they could just distill, but it's cheaper to do this. So we're going to take a look at what is a strong acid cation resin. We know what strong acids are. Well, a strong acid cation resin exchanges all of the cations for H+. It doesn't matter whether it's a calcium or a magnesium or a sodium cation, they all get exchanged for H+. Which begs the question then, is there a weak cation resin? And there is, and we find it in softeners called wax. And so in a wax softener, the wax do not exchange sodiums. They'll exchange the calcium and magnesium, but they don't exchange the sodiums. There are certain advantages to a wax and certain disadvantages. It's outlined in that paper that I put up the study notes. I'll read more about that. What do we regenerate a SAC unit with? Sulfuric acid. We start gently with a 2% sulfuric acid, and then we boost it up during the regen to about an 8% solution. Now, these particular resins are heavy, physically heavier than anion resins, and you're going to see when it comes to mixed bed, that's going to be important. We've already talked about this, and so there's a SAC resin. That's what it looks like. And it doesn't matter whether it's in sodium service or hydrogen service. Now, as for the anion resin, that's what it looks like. It's a strong base anion resin. And the SBA resin exchanges all of the anions for hydroxyl. Now, there is something called a weak base anion, and a WBA does not exchange the carbonate, and it does not absorb silica. So the super duper thing about the SBA is that it removes silica. And that's why we see these being used in thermal generating stations or anywhere where we've got a turbine, let's say in a pulp and paper plant. Very important that we remove silica And the strong base anion does, but the weak base doesn't. We regenerate this one with sodium hydroxide. We got to heat it up. It's got to be, 50 to 100 degrees Celsius. And it's a lighter resin. So we're going to leave it there. And when we meet tomorrow, we're going to talk about the regeneration process. When do we regenerate it? And we're also going to look at those other things, mixed beds, and we might also get into reverse osmosis systems.